All right. And okay, so before we start with Apache Spark, do you have any questions with respect to NoSQL, Flume, Scoop, all the things which we have discussed so far? We have come a long way. We started with the general big data description, then we went into HDFS, how does yarn work, and then how does MapReduce work. After that, Hive, after that, Pig, after that, Hive, after that, NoSQL, HBase, and then Scoop, Flume. And today we are going to start with Apache Spark. All right. Yeah. So Sandhya, actually, I just before this session, I noticed that I have not posted the course, and that's why I quickly updated. And I think now, so this one, session number 10 is June this. Is this correct? Yeah, this is the one which last session. Session number 9, yeah, 9 is updated. Session number 10 is also updated. Okay, all right. 4 and 5. Today is 4, tomorrow is 5. So tomorrow will be probably the last session. Okay, and all right. So Sandhya, things are updated now. All right. So in this case, right, Sandhya, if you notice any of the things, just drop us an email at Hadoop at No Big Data, and then we'll rectify it. All right. Okay. So we'll cover the most important thing first. All right. Now, okay. So Vikas's question is Spark independent tool or it's dependent on another? So the easier answer is both. It runs independently as well as it interacts with HDFS. Kalyan's question is, do you have any limit on minimum number of nodes that are required for forming what? Forming the Hadoop cluster? All right. Okay. So Vikas, was I able to answer your question? It basically runs independently as well as it depends on other components. All right. Now coming to Kalyan's question. So honestly, you can actually set up everything on a single node in Hadoop. Hadoop doesn't deny it. It will keep complaining that your replication factor is not being met. If your replication factor is set at 3, it will keep on complaining that we are not able to meet the replication factor. Okay. But if you reduce it to 1, then one node is sufficient and it'll be okay. But it doesn't make much sense. Uh, The Hadoop cluster, it should have at least 3 to 4 nodes. Okay. Only then it makes sense. Otherwise, it's just for prototyping and it's just for demoing purpose. And demoing purpose also, it will be actually a lot of time you will end up doing very much mistakes. Okay. Like for example, if you are building a client server application, you should always try to demo your application using two machines, one for server, other for client. Like I've had many demos where people showed the same thing using the same machine running as server and client, and they ended up making a lot of mistakes. Okay, they ended up making a lot of mistakes. So I remember somebody giving a demo that we can use a CD in a web application. Now he was accessing CD on the server side, not on the client side, and he was not able to differentiate between the two because he was just using single machine. So in the same way, it doesn't make much sense. So if you take a case of giving a demo on Flume, okay, giving a demo on not Flume, Scoop. So if I'm giving a demo on Scoop and everything is on the same machine, and I'm trying to import data from MySQL to HDFS, okay, so everything will work perfectly fine because MySQL in its default setting would allow any any local service to connect directly to the database, okay, any local service. But the moment the same program is run on a cluster, it will throw a lot of errors. So to be very frank with you, if you are even testing things, you should be testing on at least 3 nodes. All right, great question. Any other was he able to answer? All right, great. So let me see how many people are there. All right, how come only 11 attendees? There are supposed to be 25 people in this class, 20 people in the class. Probably people have realized that there is a video, so they can catch up with the video. Okay, so in recent times, people, I mean, one of the team from University of California, they came up with with a product called Apache Spark. It's called UC Berkeley, not California. It's a UC Berkeley. All right. So Apache Spark is a part of Hadoop ecosystem right now, and they claim to be faster than Hadoop MapReduce. Okay, they claim to be faster than MapReduce. So whenever we talk about Hadoop and we try to compare Hadoop and Spark, so Hadoop and Spark do not compare. It's MapReduce and Spark that compare head on. Okay, so Spark is actually pretty fast than MapReduce. They have even won a sorting benchmark prize last year, I think. Yeah, 2014 prize they have won at sorting benchmark, which was earlier won by Hadoop MapReduce. So they are pretty fast than MapReduce, and I mean, as but their claims, it's 100 times faster than Hadoop if the data is fitting into memory, and if data is being on the disk, it's 10 times faster. So it basically utilizes the RAM extensively. It builds on a similar paradigm like MapReduce. It also has got its own form of mappers and reducers. We will discuss those things. But the idea is a little bit different from MapReduce. While MapReduce was very batch oriented, Apache Spark is very real time. In case of MapReduce, what we used to do is we used to form a full batch of commands that do this map, do this reduce, and then store the data somewhere else. And in the second one, in the second second phase, we will read the data again from HDFS and then process. So this that that whole mechanism were very batch oriented, meaning get these things done howsoever possible, take your time. Okay, so that was the attitude, and that was the whole design aspect. In case of MapReduce as a design choice was built as batch oriented, meaning there is no hurry, do it but get it done. Okay, that was the general attitude. But here, in case of Apache Spark, the attitude is get it done right now or give me error. Okay, try twice, give me error, but get it done right now, don't keep me waiting. So that's the general attitude, that's the way Apache Spark has been designed. Okay, and Apache Spark is very well integrated with Hadoop. Okay, meaning inside Apache Spark. So Apache Spark runs on top of Hadoop really well, just like the way MapReduce ran on Yarn. In the similar fashion, Spark also run on top of Yarn parallel to MapReduce. Okay, so Spark can run either on top of Yarn, on top of another similar uh, resource manager called Mesos, or it can also be run in a standalone mode. Standalone mode means that it will not interact with the Hadoop or anything. It will deal with the local files. As well as it will be running as a single node. It will not be running parallelly. All right. So similar to MapReduce, if you remember when we talk about MapReduce also had libraries such as Hive, Pig. Hive was for running SQL on top of MapReduce, and we had Mahout also. Mahout was a collection of algorithm that used to run on top of MapReduce. So similar to MapReduce, since Apache Spark directly competes with MapReduce, there are libraries which have been built on top of Spark. So these libraries are Spark SQL. Shark has been outdated. Spark SQL has taken the place. Spark SQL is nothing but whatever SQL you define that gets converted into MapReduces of Spark and and get executed on Spark cluster using Yarn. Okay, and Spark streaming is another aspect which was not there earlier in case of MapReduce. Reason being that MapReduce was designed batch oriented, so it was not suitable for doing a lot of fast things. Okay, now that was Spark streaming for real time processing. Next is the MLlib. MLlib is another machine learning library. In case of MapReduce, we had Mahat. Now we have MLlib here. MLlib is far more exhaustive and far more sensible than Mahat, because Mahat was just a bunch of algorithms, a bunch of programs. That's all. Here, MLlib is more like your R. It has got things, really good things like hypothesis testing and even neural networks. So MLlib is a pretty good library. I've reviewed MLlib and I've studied it, and I found it really nice. Similar is the case of GraphX. GraphX is another graph processing library where, say, you have to compute page rank or do any kind of graph analysis. GraphX will be your choice. Okay, there we have Giraffe in case of MapReduce. Here we have GraphX. All right, so that was head-on competition with MapReduce. Okay, and those who are wondering that Mahat it competes with Mahat, it doesn't compete with Mahat. It just competes with MapReduce. And MapReduce itself has got a lot of use cases in the sense that if the data is into hundreds of terabytes, then MapReduce is actually a choice. But below that, Apache Spark will do a better job. Okay, reason being Apache Spark actually works well when we are talking about in-memory processing. So there are three kinds of processing, which is single machine in memory, multiple machine in memory, and then out of the memory. Okay, meaning when the data is not fitting into the memory of one machine or multiple machines. So out of the memory, MapReduce is still a good solution. Reason being, if you try to do heavy memory processing using Spark, it generally consumes the whole memory of the system and does not leave the space for anybody else. Okay, it's little memory hungry and memory greedy. So in case of an enterprise environment where there are multiple projects using your cluster, people still choose to use MapReduce because MapReduce will not starve other processes on that machine. Okay, so that was a little overview and comparison of Spark. Okay, so although we have already installed on Yarn our Apache Spark, I'll still give you an overview. So if you go to Spark's website, it shows you for which Hadoop you want to download Spark and run. Okay, so for our kind of case, because we were using Hadoop 2.4, this particular version of Hadoop was more suitable. This particular version of Spark was more suitable, so we downloaded that. We extracted it, we and then we just copied that folder into user lib. So this is copying the folder into user lib, and then we created a symbol link, a symbolic link. Instead of typing this full folder, you can now type just this one, and then you can well, if you're logged in as a student, you can just go to this, you can just run this command. Okay, and then you will be in the, okay, so where are we? All right, I think, yeah, we are here. So I am in this folder. Okay, so user lib spark and bin, this is the folder where all the binaries are available. You have a Spark cell, which basically runs the Scala cell. I'll explain to you, don't, no worries. And then Spark SQL is there on which you can run your SQL commands. I've never used this. Yeah, so this is started. Anyway, I'm not going to demo this. All right. So basically, to run Spark command line, you just run this. So how many of you have coded on any scripting language which has a command line? The language with a command line interpreter? There are two ways you generally program. One is using command line. You type statement by statement. It keeps on giving you the results. Other is you write the full program, compile it, and then run it. So have you ever used? Okay, Amish has used Python. Yes, Python will qualify. Perl will qualify, and even Shell will qualify. Yes. All right. So I think a better idea would be to give you a quick overview of Python. Okay. So it sounds like this course is like covering everything, but let me just give you an overview, and that should give you fair amount of confidence. All right. So, how do I make it? Let me just stretch it. No worries. Yeah. All right. Good. Good. So now we are. So this is our command line of this Spark. You can see that. So it says that Spark version blah blah blah, and here we are. Okay. So it's connected. It's yeah. So it says that it has started some HTTP server so that you can monitor it. And yeah. Now this is actually nothing but a Python command line. It's actually a Python command line. Okay. Uh, and how do I? So if you type help, yeah. So if you remember, it is basically, you can see welcome to Python blah blah blah, and it's an online utility. So it's basically a Python command line. All right. And then this Python command line, there is one additional addition, that is Spark context. One, in this Python command line, you can run any of the Python command and get your work done. Say, for example, you can use this as a normal Python program. So the simplest statement in case of Python would be just typing say 1. This is also a valid statement. Saying things like x equals to 2 means we are setting value of x equals to 2. Okay. And if we are saying y equals to y, just a second, y equals to x into 2, then we have got y. All right. So this is basically Python console, which you can utilize for immediate programming. Okay. So if you are not familiar with Python, you can basically install Python. So this is my local machine. On this also, I can run Python, and you can see the same command prompt. Here also, you can type the same thing. You can do things like x into 7, and you can see. All right. So if you don't have a calculator, you can use Python as a calculator. You can see. Okay. All right. So that was defining expressions. Now the next point is that you can basically write functions or even loops. You can start writing loops. Say while y greater than 0, print y, and then say okay, it'll take a little bit time because it's running on the server. It's taking a little more time. And then we can say y equals to y minus 1. Okay. And then you can see that it basically, we just iterated over this, and now y would be 0. All right. So you can write any of the complex Python program in onto this script, and we are still on the Spark console. Okay. None of this is happening distributively. It's just happening on the local machine. All right. So this way you can write a complex code. Next is you can define a function. So you can say def my function and say x comma y and put a colon, then put a tab. Remember the tab is important. Without tab, it will give an error. So the way Python tries to identify blocks is using the spacing. Okay, so tabs are mandatory. Now you can say return x into y. Okay, so what does my function do? My function simply multiplies two variables. All right, so you can see that. All right, so it quickly multiplies the two numbers. So in the similar fashion, you can combine functions, loops, and everything, and it will give you a really, you can do anything that you can do in any other programming language. Okay, it's fairly powerful. You can use an import command to import any library, and okay. Now here there is one object, extra object given to you, which is SC. SC means Spark context. So Python as a language is clear to you. You can start using Python in general. So we just wrote couple of statement. We wrote one loop. We wrote one function. This is probably the shortest premiere I can give on Python. Was that clear? No? So yeah, SC is just one object here. Just like you define X, Y, SC is provided to you as you run PySpark. If you don't run PySpark and you run Python, then SC will not be available here. Now coming back to another question, SC, full form of SC is Spark context. Okay. Now the other question is, basically a Spark is based on Python. No, Okay, it's not based on Python. It's just that people have done the binding such that whenever we are executing anything on SC, which means Spark context, it will be calling Spark functions. Okay, Spark is written in another language called Scala. Okay, it's like running Java program to call the C libraries, or running Python program to call C libraries or Java libraries, or here we are calling Scala libraries. All right. Now, next question from Aruna is Python needs Spark? Not really. Python runs independently also as it's running here. You can see that. Same code will run here also. Just that in case you want your program to be executed on multiple machines, then Spark is a good way to get it done. All right. So anything you do on SC that will be executed on Spark. Okay. SC is the Spark context object here. Context meaning it's an entry to the Spark. That's the single object, single entry to the Spark from the Python side. Make sense to you? Any questions here or with respect to Python? So we just went with a very basic thing, like you can define variables, you can assign to variables, you can define expressions, you can run loops, you can define a function. That's what we just did. Okay. Any questions on this? Aruna, Bashant, Diya, Kalyan, Kirti, Lingli, Ramesh, Sandhya, Vikas Mishra. Yes, Spark has multiple language bindings. You can write, you can interact with the Spark using Scala. You can interact with the Spark using Java, and you can interact with the Spark using Python. All right. Vikas, Gandham, and Vikas Mishra, are you with me? Lingli. So should we move on? Because this small knowledge of Python will go a long way. What we just did. All right. Great. Great. All right, so far it was pure Python. Now let's talk about this Spark context. But before talking about Spark context, let's just go over a couple of basic concepts which are new in case of Spark. All right, so here we are. Can I hide my notes section? So speaker notes, so spelling suggestions. All right, I think this is better. Cool. All right, so the basic concept on which Spark relies is the concept of resilient distributed data set. What does it mean? It means that creating a virtual array kind of a structure to represent your data even if the data is lying on multiple machines. So those who are familiar with R kind of a language, R or any other data oriented language, everywhere we have been first defining data and then doing operations. If you remember pig, first we loaded data, then we did filter and other operations. In the same manner, here the first thing we define is how to create the data. Okay. Yes, in SAS also it's the same story. Good. Thank you, Kalyan. And so so first of all, we define a distributed resilience data set. And okay, so resilience dataset basically indirectly represents data which is located on multiple nodes. Here you can see that this is divided into four sections. So one section would exist on one Spark node, other section would exist on other Spark node, and third one, fourth one. This way, utilizing the RAM of these four machines. So this particular data set is spread over four four different machines and utilizing the RAM of these four different machines. Okay. Also, in case one node fails, okay, in case one node fails, the resilience dataset will quickly recover from it by utilizing some other machine instead of the one it was using earlier. And it can have any data type. It can have any data type, just that it will be an array. It'll be a big array. RDD is like a big array which is spread across multiple machines. So generally it can hold any kind of data, and each element can either be just another object or it can be just a primitive value. Okay, so in case you are trying to represent a big matrix, each element could be a row or each element could be a column. Okay, and then it will be made up of rows or columns. So the basic thing to remember is RDD is a big array. All right, it supports, this array supports kind of operations on top of it, the way we did operation in case of pig, saying this is my data set, can you filter, or can you just dump, or can you store it somewhere. Okay, so there also you must have noticed that on some operations, or when you do filter or when you do group by, nothing was actually happening on the ground. It was just pig was just making note of it. And there, when you should say dump or when you say store, then the action was happening. Similarly, here also there are two kind of operations called transformation and other is called action. We will go into details of each. All right, now let's try to create our usual thing. So this first line here, okay, this first line, let me just show it in a text editor. Okay, so this is the first line. It says that it says that this lines object equals to lines equals to sc, which is spark context dot text file, and then we provide the full argument as the hdfs file. So what does it mean? It means load this file from hdfs and create an rdd called lines. So these lines will be in RDD, which will be representing our big.txt in HDFS. Okay, so let's try to create it. All right, so it has created a RDD for us. Okay, if you say here lines, so it shows you that this is the mapped RDD. All right, next is Next, you can, if you have just an in-memory object on this local machine and you want to push it. So let's say you had this big array here, although this is a very small array, you had a local array which you want to push it to the cluster, which is Spark cluster. You can simply say, my array equals to sc.parallelize, and that's what you have, my array. Okay. All right, so this way we have created a text file, two RDD. One was lines from HDFS, other was in from the in-memory object. So you can create an RDD from many different file systems, many different places you can create RDD from. There are many different kind of loaders, and you can use those loaders to create your resilience data set. All right. So is RDD concept clear? Now, once we have created these two RDDs, lines and myArray, then we can start operating upon these two RDDs. Okay. Any questions on this? No? All right. Let me try to explain the second line again. So here what we are saying, the way we said earlier, Spark context, please create an RDD from this particular text file. That's what we said earlier, right? To Spark context. Now we are saying Spark context, please create, parallelize this particular array which is in memory, meaning create a resilience data set out of this array, meaning this array will be pushed to the full network and then we can start working on it. Yes, so we are loading data here. This is what is loading here, Aruna. So we are basically loading into this. So these lines basically mean that we are trying to load the data. Similarly here also we are trying to load the data. Now lines and myArray will be the data sets or RDD on which we can do the operation. Now what is this array used for? This array basically, if this array, imagine this, if this array is 100 GB, okay, and your local machine is not able to handle 100 GB, or you want to do an operation which requires 20 such arrays to be loaded. Okay, so you first load it into memory, then you kept on pushing into the Spark. That way, that way you can create this RDD and you can do an operation. So these are just examples for the heck of it right now. We have taken just few elements here and try to load. Okay. Ideally, in case of big data cases, these arrays will be in gigabytes. All right. Did they confuse you, Vikas, Aruna? Okay. So concept is very simple. You take the data and load it. That's what we are saying. Here, this is like loading a text file. sc.text file means load this text file into and give me the reference back, which is give me a lines object. So lines is an RDD. Here, similarly, we are saying sc.parallelize means please load this data which is in memory onto my Spark cluster. Okay, so you can imagine this way that okay, so you can imagine it this way. Yes, no, only one command. Each command is creating one RDD. So this is creating one RDD. We don't require two commands. This is just I gave you two examples. Okay, so this is okay, this is creating lines RDD from an HDFS file called big.txt. Okay, and this one is creating the myArray RDD from an in memory, as in it was loaded on this computer's memory. Okay, memory array. Okay, makes sense to you now? All right. So basically what we did was, so if you remember in HDFS, we had these blocks and in case of RDD, so each block would be loaded onto one machine in the cluster of Spark. So this upper block represents the cluster of Hadoop. This is basically a cluster of, this is Hadoop cluster maybe. Okay. HDFS cluster, node 1, node 2, node 3, node 4. These are four nodes, and this also is another cluster of Spark. Okay, this is Spark cluster, and is having 4 nodes. Each node is loading data from HDFS. All right. All right. Now, so in this exercise, we will do our typical word counting thing and we'll do few more exercises. Now, what can we do on top of RDD? Resilience distributed dataset. This is RDD. This particular lines object is not located on local machine. The way we dealt everything in past, always we had data loaded into single machine and then we operate. You can think of lines as if it's a handle. The way you have connection object open, you have connection object in databases, right? And on that connection object you can do multiple kind of operations. In the same fashion, this lines is your gateway to the Spark RDD. All right. Now what can we do on this object? Okay, or what can you do on RDD? The most simple one is transformations. You can transform one RDD into another RDD. Okay, so this is your command line. From here you can tell RDD to do a transformation and it will create another RDD. Okay, now first I'll try to do a simpler one. All right, let's say this is one of my RDD. My array is an RDD. Basically my array is an RDD. Now let's say I want to do some operation on my array. Let's say I want to square all these numbers. Okay, I want to square each number, which means 1 will remain 1, 3 will become 9, and 5 will become 25, 6 will become 36, and so on. All right, that's what I want to do. So and that's where we use the transformations. Okay, so transformation, so this is us, this is our command line. Okay, and this command line is launching a transformation on RDD, and this will create another RDD. This will create another RDD, and will say that after creating that another RDD, it will give you the reference back. Okay, now what kind of RDDs are possible? Let's take the first case called map. Sorry, not RDD. What kind of transformations are possible on RDD? So first transformation and the most simple one is map. Okay, this map is a little bit different from what we had studied in case of MapReduce. Okay, we'll keep that aside for now. And whenever we refer to map, it's a little different thing. Map means map. Every time we call map on an array, we pass a function pointer. Okay, meaning this is your machine. So what we are telling, this is your function. We're telling to map that hey, this is your function. Take this function and run it on each element of an array. Okay, so if we are saying something like my array dot map, and we say square. Okay, this will give us my squared array. So what will happen is this this square function will be taken to each of the array element and then will be applied on each element. So map will apply on each element. Okay, so any function, anything you give here, if you give cube here, so it will return a new array containing a new array containing the cube of each element. So whatever function you provide here, it will be run on each element and the result will be stored in the output. Okay, so let's try to do. So let's first create or do we have a square function? I'll just try f square. We say math.square, math.square. All right. So I think we'll have to create our own function. So map has to be used in an, yes, always map function has to be used on an array object. Instead of you iterating, so in typical sense, what we used to do, we'll write a for loop which will iterate over an array, and then we will run each element of the array through a function, right? If we have to process each element of an array, instead of doing such kind of operation, instead of you iterating using for loop, while loop or something, you use map function. Map function will take whatever function you are providing. So map will take whatever function you are providing an argument, apply this function on each element in an array. Okay. All right, so I think a square function is not there. So I'll just write a quickly a square function. So let's say define a square, and we say square and return x into x. Okay, now you can say square, and whatever value you pass into this function, it will square that. Okay, so we just wrote a very simple function which does the square of any number you pass as argument. So this function is clear to you, what we did just now? Is this okay? So we said def, meaning defining a function. Then we said sq, that's the name of the function. And then we provided an argument x and returned x into x. Okay. We don't have to define the data types in case of Python. So is this clear? How are we computing a square? If this is clear, then only I will move ahead on to applying it on the RDD. So does the data always go through HDFS? Does the data always go through HDFS first, then Spark? Yeah. So in our case, when we are loading data from HDFS, in those cases, we are basically saying that we will put our files in HDFS and then load it into Spark. All right. But Spark can load data from variety of sources, not only HDFS. Now coming to Kalyan's question, map can't be used in line. Am I right? In line as in, if there is no array, map cannot be used on that. Mhm. Map can be used, yeah. No, but map expects a single value which can be multiplied and returned. If we pass our array into square, it'll give an error because we cannot multiply line with a line. Okay, but each element of my array can be passed to square and then done the operation. I think that's what you meant by your statement, Kalyan. All right, so if this is clear how we have defined a function and how we are executing, is this clear to everyone? Yeah, please feel free to ask questions and interact, because this does not require too much of knowledge of previous sessions. And in case there is a doubt, the doubt will be genuine. So doubt will not be because that you have not been able to follow up with the previous sessions. So please don't keep that in mind. Okay, because we are not reusing anything from our previous sessions. So this function is defined in Python right now. Okay, so we said in Python saying define square x colon, meaning our function body started, then a new line, and then press tab and then return x into x, meaning this function will be returning x multiplied with x, and then square of 10 is 100 and square of 13 is, so our function is working here. We are calling our function what we've just defined here. All right, this is the definition and this is how we are calling. Is this clear to everyone? So Amish, Aruna, Basant, Dia, Kalyan, Kirti, Lingli, Ramesh, Sandhya, Vikas, Gandham, and Mishra. All right. So looks like everybody is with me on this. Great, great. Now, so this is the so if you have a doubt, just keep on asking, because if there's a doubt, it'll be genuine doubt. It would not be because you could not pay much attention to the previous sessions. All right, great, great. All right. So now the next thing is, what we want to do is we want to do the square of the full RDD. Okay, this is our my array. My array is an RDD. If you want to see what's there inside my array, we can say my array dot collect. Okay, it will bring the my array, which is distributed on the cluster, onto the local machine. And you can see that now it has done some processing and brought back all the values of this array to the single machine. Okay, so my array is on multiple machines, so keep that in mind. Now, on my array, if we want to run a particular function, so we define square. Okay, so we are saying my array dot map square bracket start, not square bracket, round bracket started, and then sq, and then this. So what we are saying is, please apply my function sq on each element of my array. That's what map function does. Okay, and this will give us a new RDD. So every transformation gives us a new RDD. So we can say squarr. All right, now squarr is this. All right, we can check whether it is. So squarr is just a pointer to our RDD. If you want to gather all the elements of this newly created RDD, we will say squarr.collect, and it will bring all the elements from our data set, which is distributed across the cluster. All right, now you can see that. You see that? So it is squared each element in place. So this is the map function. This is the map transformation. It transforms each element of an array, which also means that any function you are passing to map has to take only one argument. Okay, only then it means something, right? Because this map function has to take one value and give out one value, and the output of all the executions of this function will be collected, and a new data set will be created. Okay, is this clear, the map function, the map transformation? So yes, we defined a function called sq, okay, in the previous exercise, and we created my array earlier, and now we created, okay, my this thing is running a little slow. So this is what we did. Okay, this is what we did. All right, so what we did, we first created this in the previous step. We created this, and then as a next step what we did was define a square, which takes an element and then multiplies it, returns it. So it defines a square function. Then next step, we basically did this. Okay, are these three steps clear? All right, great question. So let me answer Kirti's question first. So Aruna, is that clear now? Yeah, no. What is the map? Array map is transforming. So okay, again, so what is my array? My array is nothing but a data set which is distributed on multiple machine. It is not like a usual variable. It is a Spark RDD, which is nothing but a data set distributed on a cluster. The way when you create a database object and database handle, you have this cursor, right? cursor does not contain any data, it's just a pointer to the data. Similarly, my array is basically a pointer to the data which is lying on multiple machines. Now what you do is we say my array, and we run a function called map on top of my array, passing the pointer to this function which we have just created. We are saying please apply sq on each element of an array. Okay, and whatever is the result, store it in sqarr. Okay, so this map function is transforming my array to produce a new array. Okay, so here the code is being transferred, meaning this map function will take your square code, whatever is the code inside square function, and will take onto each machine on which your data set is there, and will run on each machine and transforming each element into a newer element. That's what it is doing. Aruna? The value of sq function to sqarr. So no, it is transforming my array into this. So what will happen is map function will take your square function first to this, then to this, and then to this. And therefore, when you say sqarr dot collect, okay, you get you get these values. Okay, all right, here. So this is what gets transformed. So when sq was applied on first element, the new element is 1. Okay, sq of 1 is 1. Sq of 3, when sq was applied on 3, it becomes 9. So basically, what did Spark do for you here? Spark is doing all this magic for you. I- Spark provided you a function called map. What it does is it takes any code you do any code. If you have written a cube function or a square root function, any code you have written here, it takes to each element and transforms it into a newer element. All right. Now, where is this SQRF? As I just told you, that SQARR is again a new RDD, which is just like my array. It is also distributed on multiple machine. That is why if we have to print it, we have to collect the data from all the nodes and bring it here. Okay, all right. Is this clear to everyone? These are most simple example to understand the map and so lifespan of an RDD is an RDD is alive as long as your client command line is open. As soon as you exit the command line, these RDD will be destroyed unless you say rdd.persist, in which case even if you exit this command line, it will remain alive. Very good question, Kirti. Thank you. All right. So so again for those from here, this is our client application, this is our entry point, this is, we call it, in terms of, if you see the presentation here, it's a Spark driver application. It could be Python command shell, Scala shell, or any other like Java machine. So from here we are controlling our cluster, we are passing the commands to do things on the cluster, and we are it's like a DJ controlling the crowd. Okay, so it's the same way. And all right, so Kirti's question is, how does data gets distributed on different cluster? Okay, so I mean, that I'll not go into the details of how does the data get distributed. The general strategy in case of we are loading a text file, so one line will be element. So each element is non-divisible. In case of Spark, one element will always be on a single machine. So if your single line is such a big one that it is having like 5 GB size, it has no new line, so in that case a single Spark node will be overloaded. Okay, so in the way it is done right now, when we say sc.text file, the file which we are talking here is in HDFS, so it will try to load that file onto the cluster line by line. Each line will become an element in an array, in an RDD, and in case our line is so big, in case our line is so big that it is not fitting into one memory, then it will give an error. All right. All right. So in that is the case of sc.text file, but the method of loading different kind of data will be different when you're loading from different sources. All right. So is everybody on single page, or have I disconnected at at any point? Feel free to ask anything right now, because if you don't ask now, you'll get into this mode that okay, I'll watch a video later. Okay. Aruna, are you comfortable? And Lingli, Kirti, Ramesh, Sandhya, Vikas, Amish, Basant, Dia. All right. Keep asking. I mean, so Aruna's question is, when would we pick Spark over other technologies? So generally for your data size, a kind of data size which is which can fit over. Okay, so let me again take a step back. So if your data is small and you are pretty happy with your single machine, you don't use a Spark on any of the technologies which we have discussed in this full session. Okay, if you are if you are happy with the single machine. Okay, the moment your data starts becoming big, the ability to read data, meaning your drive, will become inefficient because it takes the hard disk itself is a bottleneck, then RAM will become bottleneck, and then your CPU will become bottleneck. In those cases you use distributed technologies. Now comparing the MapReduce and Spark, so whenever you require the immediate response, you go for Spark. In case your data is actually beyond some 50 terabytes or really really huge, then you generally go for MapReduce because that doesn't consume too much of RAM. Okay, so but in general in today's time, mostly you will be able to get everything done on a Spark cluster. All right. All right. So that was Aruna's question. Coming back to Kalyan's question, let me rephrase whatever I discussed. So I think a better strategy would be to show you. All right, coming back to Kalyan's question. So when we did this, we said line equals to sc.text file, and we tried to load this. So we had line, okay, line, and let's just try to gather only first 20 elements of line. So by saying take, we can say lines dot take and say 10 or 20. We will be able to peek into what exactly is there inside lines. Okay. So it will basically show you the top 20 lines in an array. So if you look at it here, it looks little ugly, but don't mind that part. Okay. So from here to here, what does it have? It shows you the square bracket, and then U means Unicode, and then up to comma. From here to here, Okay, you can see that. So this is one element of an RDD. This is another element of this RDD. This is third element of this RDD, and so on. So basically, this lines here, let me just make a lot of space here. So this lines is nothing but top 220 lines from that file. Okay, so which effectively means lines is an array containing is an array of objects, and each object is a string, and this string is nothing but a line. Okay, so it's an array of lines. So that's what happens in case of when you try to load the data. Now coming back to your question, now in case this line is bigger, so the way it is done is this line will have, say, line has, say, how many lines dot size, lines dot, there is lines dot, what was that, lines dot count. All right, so lines dot count will return total number of lines. So let's say it has 1 million lines. Okay, this file has 1 million lines. So maybe first line to 100th line, so lines is an array of 1 million strings. Now this will be on maybe on machine 1, and from 100 to, say, this is little like this. Okay, so first 10,000 on one machine, second 10,000 on another machine, and so on. Okay, so this particular portion is actually loaded into this machine. So in case this array is so big that it can't fit into memory, then you'll get an error. In those cases, you have to tell Spark that, hey, my individual line is really big, so make sure that you are able to handle it. In that case, it will try to serialize it and keep some part of each object onto the disk. Okay. Kalyan, was it clear? No? All right, great. Now, live data like on real time, yes. So lots of everything, whatever we are doing actually is happening in real time. Okay. So everything, so here it computed the line and we are getting immediately the answers. We are not, scheduling things. Here things are happening in real time. All right. So is this clear? Now let's say we want to convert. Okay, we will again come back to this problem. All right. Now there was a function called map in which each element was of an array converted into another element. Now question to all of you is, as of now, let us say we are doing this. Okay. So question to you is, if my array had 50 elements, how many elements would SQ array have? Okay, anyone? Great. Okay, great. So it will have 50 elements. Okay, so it's a one-to-one mapping. Now if we have to convert our line into words, multiple words, then this will not be a great ideal solution. All right. Next is that in case we want to just keep few elements of our array in the output, then we can use filter. Let us say out of this array, we are only interested in elements in the elements which are which are odd. Okay, so let's say we define a function called is odd. Okay, and what does this do is it returns true or false. Okay, in case when you divide a number by 2 and the remainder is 1, x percentage 2 means when you divide something by 2, whatever is the remainder, and in case that is equal to 1, then it will return 1, otherwise it will return 2. Okay, it will return uh, false or true. Okay, I'll show you this. So you can test is odd by running is odd on 1 and is odd on 2 and is odd on 0. Okay, so it's a little slow. Maybe the network is a little slow. Why? Oh, terminal has quit suddenly. No worries, we'll just start the terminal again. All right. Sorry. So I'll have to run PySpark user lib spark bin PySpark. All right. The only problem is, so this object is now lost. If you so so you can try my array, it says not found. So let me just do whatever we were doing. Okay, now let's say we want to just keep those elements in a new RDD. We want to filter those elements out of this my array. Again, my array is distributed, so we want to just keep only those elements which are odd, which means 6 will be removed. Okay, 6 will be removed. Okay, now what will we do here is, first let's define a function called is odd, then we run. You can see it's working so good. Now this is pretty fast. Okay, so in case of even, it's returning false. In case of odd, so our function is working perfectly. Now let's launch it. Let's send it to the cluster by saying my array dot filter and is odd. What will it do? It will basically, so let's just create a variable called only odd. Okay, so only odd is another RDD. So what does it do? Filter will basically take your function, run it, run this function against each element of my array, and whosoever element is returning true, only those elements are kept in the output. Otherwise, that particular element for which is odd returned false will be dropped and will not be kept in the output. Okay, so only odd, if we say only odd dot collect, it will basically give you these elements. Good. Okay, so what we did was, again, all right, so only odd has what all element? This elements. Perfect. Everybody okay with me? So this way, so all right, so question to all of you is, only odd will always have less than or equal to my array. Correct. So this is the statement is true. Okay. So this way we have taken the processing from local machine and handed over to the multiple machines. Imagine that you had to compute really complex things, meaning something like cube root. Okay. Then computing cube root is little more intensive, and instead of doing it on a single machine we have delegated it to multiple machines, so we can run a map on cube root and which will cube root all the elements parallelly on variant machine. And remember, we are not bringing the data back immediately, which means there is no data transfer happening. The only cost we would incur is while loading the data. Loading the data is the only cost we would incur. All right. So that is filter. Now flat map. Flat map is similar to map function. It can return multiple values for each element of an array. Okay. So we'll use flat map. Again, coming back to our lines. Lines contains an array of lines, and we want to convert each line into a word. So what we will do, we will define a function. Okay, we call it say two words. Okay, what does it do? Given a line, it would convert it into words. Okay, line dot split, and this function is in Python. All right, now you can see that. All right, so two words. Let's test this Python function which we have created. This is a line. Okay. All right, let me just close. Yeah, so it has converted a line into an array of words. So this function, this function called two words can be used in flat map so that each line will be converted into words and the resulting array will be an array of words. Okay, so in case of flat map, what we do is we we take I mean, let me just say okay, we call it words equal to lines dot flat map, and we pass two words. Okay, so this function called two words will be applied on each of the element of lines, and then whatever is the result, expected result from this function is an array, and then those words, those objects, those elements will be kept in the output. Okay, now is the flat map clear to all of you? So firstly, let's again load because we our this thing exited. All right, so we loaded our text file, and now we are saying flat map. Okay, is everybody with me? So in the first line we said please load our text file as lines. Now we converted lines into words by using this particular function. All right. All right. I hope I'm not making it a little mess. So here I'm saying that load my file, and then I'm running these two words using a function called flatmap. And these words, let's have a look at words. So whenever you're dealing with big data, you generally don't collect everything. Instead, you just take few elements to test what is there inside that particular. Now you can see that it is the each word as a separate object. Okay, each word as a separate object. So our new RDD, instead of being an array of lines, now it is array of words. Now let's say we want to translate each word into lowercase. So what will we use? Will we use map, filter, or flat map? If we want to translate each word into lowercase, what will we use? Map, flat map, filter. Anyone? Great, great. So we will use map because we want to, it's a one-to-one relationship. Input is one value, output is one value. All right, so let's say, uh, okay, so lower, let me just test. I'm not that thorough with Python, but I'm fairly comfortable. All right, so let's define, we call it my lower, and whatever word we pass to it, we say return w dot lower. Or we can actually say, does it work like this? I doubt. Yeah, I think it works. No, it's not working. Yeah, this one works. So we'll have to say w dot lower. So we defined our function, okay, which basically converts anything into lower by calling a function on the string. Okay. Now what we are trying to do, um, we will basically run things like equal to words equal to words dot map and my lower. Okay, sounds good. Let's check what's inside this. We'll say take 20 instead of gathering everything. Now you can see that it's in the lowercase. Perfect. Perfect. So we have translated our data into lowercase. All right. In case we want to remove, if we want to remove all the uh, all of these words, the, is, am, are, a, so what will we use? Correct, we will use filter. Perfect. So everybody is in line, so whatever we have studied so far is good. All right, the next thing is a next form of transformation is group by key. Okay, we will talk about group by key maybe later. Okay, and group by key basically takes each element and groups it by a particular value. Okay, groups converts the full array into groups. Okay, but before that we have to convert each element into a tuple. There is a concept of tuple in case of Python. Tuple is like whenever you have two coordinates, if you have two values, you generally, or you have multiple values, you generally put round brackets around it, and we call it a tuple. Okay, so I'll show you this. So there is a concept called tuple. So if I can say x equals to bracket 2 comma 3, it sounds like an array. Okay, okay, it looks like an array here. Okay, and you can always think like an array. I mean, describing you the difference between tuple and array will be little too much here. So the concept of tuple is same as what we have studied in pig. Okay, so yeah, so if you convert your each element into something like a bracket and word and the count, okay, then you will be able to group it. Then you will be able to group it. So if you are able to convert each element into this key value, then you'll be able to use the group by key. Okay, and then you can basically run the reduce function and do the summation. All right, we'll talk about it again. So everybody comfortable with transformations? There are other transformations. You should have a look at other transformations such as sample, union, intersection, distinct, group by key, reduce by key, sort by key, etc. All right. So now, so this was transformations, and a transformation resulted in another RDD. It did not give you any result. The result was given to you by a function like take. Whenever we said take or collect, or when we said length, or not length, count, take, count, or collect, those did something. Okay, it did something, meaning it started the execution. If you see here, the moment we here, if you say, the moment we say take, it actually started the process. You see the log messages, while when we said a transformation, it did not do much. It just made a note of it, that hey, I have taken a note of it, I'll do whenever it's required. And this is very similar to what pig provided to us on top of MapReduce. Okay, now these things like take, collect, these functions which cause the RDD to be collected on a single machine, or something to be happening to convert back an RDD into a value. These things are called actions. You can see in the diagram, whenever an action happens, the data is gathered back at Spark driver application. Okay, so one of the actions is reduce. What does a reduce action mean? Reduce action means that it will call this function on only two values at a time. In case of map, the map function was map or flat map was always called on a single element at a time. Similar was the case with filter. Okay, but in case of reduce will be called at two values at a time, recursively, infinitely recursively, until the whole thing turns into a single value, until the whole array becomes a single value. Okay, so I think I have something. All right, so reduce function is like your combiner. The only difference between reduce function and a combiner is that reduce function only accepts the accept the function argument which take two values at a time. All right. So let's say reduce functions are used for aggregation. Okay. Reduce functions are used for aggregation here. So in case you want to do say again, in case of only odd, if you want to sum up all the elements, then you can use the reduce function. Okay, only odd. Do we have this element here? Yes. So if you want to uh, do the summation here, so what we will do, we'll define our add function. Do we have add here? there is no add function. We'll say x comma y, and what does it do? It returns x plus y. Okay. Now let's define this function. Now whenever we say add 3 plus 4, it's the sums it up. All right. Now let's execute the final value. So we say equals to we say only odd, and then we say on only odd dot reduce, and then we pass add function. Okay. So what will it do is it will take add, first apply it on two elements, then next two elements, and then this will generate total three elements, and then it will recursively apply on rest. So 1 and 3 will lead to 4 and 4, and this will lead to, okay, I think I'll just draw it. Okay, so 1 3 5 19 20. So we have 1, we have 3, we have 5, and we have 19, and we have 20. Not 20 but 21. Okay, so when we say add, our add function will be applied on these two at a time. And so when we apply add, it will lead to a called newer value called yeah newer value, and similarly these two. Okay, and then this will remain as such. So after applying add, it will become 4. It will become 4, and it will become 19 plus 5, how much? 24. And this will remain like this. Okay, so add is being applied on two values at a time. Similarly, whatever function we had defined in case of reduce, it will be recursively applied in the same fashion. Had it been multiplied, square root of summation, so divide a by b, and so on, it will end up giving this. Okay, now these two will again be summed up. Again, add is being called again, and so let's say 24 by 4, 28, and then you have 24, these two values, and the summation is 49. Is that clear? How is it happening? So these are called commutative and associative relationships. So the function, whatever function like summation, count, and whatever you want to use those functions should be commutative and associative. Only then it will give you the correct result. All right. Similar to what we discussed during combiner time. All right, because there is no guarantee that these two elements will be picked up first, and these two elements, the other situation could have been very, very different, meaning there could be a scenario where how do you generally, okay, so all right, how do you do the selection here? All right, so let me just copy these to a newer. All right, so the situation could have been very different, maybe these three elements could have been picked up first, and this, okay, and these two, and then with the resulting one, the uh, I mean there is no guarantee that which two elements will be picked up in what order. All right. Therefore, you can only have few specific functions, not all kinds of functions, which can be applied as reduce. All right. So reduce is one form of aggregation. Count is another. Count we have already seen for counting number of elements in the RDD. Collect is to gather all the elements on the single node, and take is to gather all the elements on this machine. Now here, whenever we said when we going to apply this, where is our function? Yeah. So sum equals to only odd dot reduce. Yeah. So it executed thing and resulted in 49. All right. Okay. So if we define something like average x comma y, x comma y, and we say return x plus y and divided by 2.0. Okay. I'm using 2.0 so that, so will it result in correct value? Anybody? Yes. So this is not average. Question is a valid, is average a valid uh, reduce function? So answer is no. All right. Next question is all right. Now let's say we define another function, myfunc, and it takes x comma y, and it returns square root, or it just return x into x plus y into y. Okay. Or yeah, I think I think you all understand. I don't need to describe this. Okay. So is this clear to everyone? There are other reduce functions other than our normal other actions such as collect, count, take, and there are more functions like first, take sample. If you remember sampling, take ordered as in take the element in the ordered, or save to the particular path. If this path starts with hdfs colon slash slash, it will try to save it into hdfs. Otherwise it will try to save in whatever form you want to save it to. Okay. So everybody clear? Now there is another function called which is not mentioned here. It's called, okay, it's called reduce by key. Okay. So reduce by key is, it will group and then reduce automatically. Okay. So we can use reduce by key for counting the values. Okay. But reduce by key, you need our data to be converted into key value pair. Okay. So here uh, we'll write another map called 2kv. Okay. Which takes a single word, and convert it into a tuple. Okay. Which says return w comma 1. Okay. So it will basically return a tuple. So whenever uh, so we can say tuple words equal to, or we can say words, whatever name we want to give, we can give here. We can say l words dot dot map and 2kv. So we have converted into key value, and then we are saying result equals to words kv dot reduce by key, and we are using our add function, which will basically will sum up all the values for this key. All right. So let's define the 2kV here. Okay, so 2kV, let's try calling on a simple word like this. Okay, good. And then we try to call it on this. And let's check what's there in our 2kV by saying 2kV dot take 10. Okay, so now each word has been converted into a tuple. Is it clear to everyone? So now our array is an array of elements and each element is a tuple. Okay, this tuple can have multiple values. All right, now let's call our another function called reduce by key and let's see if it works. No, this is wrong. All right, this is correct only. What are we doing? Result dot collect or take 10. Take 10. Yeah, I think it should correct only. Yeah, so it has basically counted the frequencies of the words. So scold has been used 3 times and all right. All right, so you can see that. Or we can say result.collect and it will give you all the result. Okay, you can see that incline can be used 8 times and so on. Okay, so basically here results.collect would give us the answer. So everybody clear about these statements? So I'm sure up to this line everybody is clear. Are you guys with me? So everybody, oh great. So reduce by key basically says group it by that particular first word, whatever word we have, and then call call this aggregation function on the second values. Okay, that's all it does. Perfect. So we'll take a rest of the session after the break, and we will be back in 10 minutes. Okay. Hi everyone, should we start now? Great. All right. All right. So, in the first half, we talked about the basics of our Spark actions and Spark transformations, and we were able to do word count problem using our transformations and actions. Okay. And that's how almost everything at Spark is modeled around, starting with normal things like um, counting, doing the matrix multiplication, doing everything is done in the same mechanism. Okay, it is done in the same mechanism, the way we have just done. All right. Now, other than these actions and transformations, Spark also provide you few more facilities. Okay, one of the facility is ability to do the broadcast of the variable. If you remember, when we had a discussion on MapReduce, our mappers were not able to communicate with each other. Each mapper was running in the isolation without knowing that which mapper it is, or without being able to communicate to other mappers. If it had to communicate, we needed something like a zookeeper or something like a database or something, a centralized service to make that happen, and which becomes very inefficient when we talk about humongous data. Okay, so in case of MapReduce, we always face this challenge that how will my one mapper coordinate with other mappers. Imagine that we want one mapper to stop, all mappers to stop processing as soon as any of the mappers encounter the word called the, T-H-A, the, T-H-E, the. In case any of the mappers get a signal, finds a word that the, it wants to stop all the other mappers involved. Okay, to facilitate such kind of communication, there is broadcast variables. Okay, there is these broadcast variables. So what happens is that these variable, so whatever variable you create, that broadcast variable will be made available to all the nodes, irrespective of whether it's on the local machine, remote machine, or some other machine. The same variable will be made available to all the nodes. Okay, and in case somebody wants to broadcast, they can simply set the value, and that variable will be updated all across the cluster. Okay, so in our case, we will basically inside our somewhere in the mapper function, what we will do is inside the mapper function, we'll say if my word equals to the, then just broadcast I have found the. Okay, and inside mapper itself, we'll put another condition. If somebody has found the, then stop. Okay, so that is something which is really important. Okay, so okay, so these individual Spark launches, so if you remember our actions or our transformations, they were running independently on each section of the RDD on different nodes on which our Spark cluster is running. And this Spark application is what we have the code. Okay, now this each of the Spark application can either broadcast or can receive a broadcast, I mean, of course, every node will receive the broadcast. They can also broadcast. Okay, so let's say this is Spark application encountered the the, and it wants to broadcast, yes, I found it, yes, I found it. Okay, while every one of these is continuously checking that particular broadcast. If anybody has found it, then I should stop. Okay, so all of these node will be running the same logic. Okay, in which we say that in case somebody has found it, then please stop. Otherwise, if I found it, I will announce it. Okay, so everybody else can stop. So those kind of cool things you can do using broadcast variables. Is the meaning of broadcast variable clear to you? No. So it's clear to only Vikas? Yes, broadcast variable can be set at the runtime. That's correct. So whatever value you are setting in the broadcast, that's the value, that's the return value. Whether it can be a complex object or it can be a primitive value. It can be like number, like 1, 2, 3, or a string, or anything. Or it can be a complex object, or it can be an array, or it could be anything. All right. So everybody okay with this? All right. Then, although the broadcast variables are good, it's just that broadcast variables are not very because broadcast variables takes little bit time to put things into effect. Meaning, meaning that the moment one of the node raises an alarm that that I want to update, the broadcast variable, all other nodes or all the nodes in the cluster will be immediately informed that this particular broadcast variable has been changed. Okay, therefore everyone will stop and wait till the new value arrives. Okay, so broadcast variables take a little bit of time and are more intensive. Now if you have a small requirement like collecting the progress of all the nodes, there's a unidirectional flow of data. Okay, meaning the data is only flowing from the nodes to a central place or to the application launcher, meaning our command line. If we just want a single directional flow, then we use something called accumulator. Accumulator is something like they keep on printing that consumed one, consumed one, consumed one, and that gets accumulated, and you get the final number. This is the progress so far. Okay, so accumulators are used to report the progress, to report the log messages, and other kind of thing. Okay, so those are called accumulators where there is only a single directional flow. All right. Now, if you had to, so this is word count example, the one which we did. In case we had to do it using accumulator, our accumulator will look like this. So where is my, all right, where is the, I don't see the broadcast function. Yeah, here is my common broadcast, and this common function will be made available to everyone. Okay, all right. So Or let us just revisit our variable here. We define, so this is our normal uh, word count example, and we define something called broadcast. Okay, so we say sc dot broadcast, and by default we put true my broadcast. Okay, so we are saying this is my broadcast variable called my b. Okay, and next is that here this my b can be used here or here. Okay, we'll say if or where is my flat map? Yeah, two words. Okay, so we can say line dot contains line dot contains the. Okay, if line dot contains the, then my b dot becomes value becomes false. Okay, and if my b dot value equals to false, then we return. Yeah, so this is the kind of logic that is generally prepared. So we initialized our broadcast variable with some value. Okay, and then inside our processing, the first mapper we are using, inside this we are saying if my b dot value equals to false, then return empty. Else, okay, else it goes down. And then in case it notices there is a word called the, then it returns false immediately. It informs this, and also it returns empty. Meaning stop processing if you encounter the word the. So this way, now that's all you have to code. Okay. Now using this, you will be able to coordinate amongst multiple mappers which will be running. Okay, and thereby, because this same code will go into all the nodes. All right, so everyone with me? No? Is this function clear to you? No? So the meaning of broadcast is we are able to broadcast to a central variable. So this variable called myb becomes like a central variable. Okay, no matter, because these two words, this function whatever we are going to run in flat map, it is going to run on multiple machines. Okay, flat map is going to run your function on multiple machines containing the RDD. Okay, because your database data set called lines is spread across the machines, right? So if there are 15 machines participating in the participating in the lines, meaning this lines is distributed across 15 machines. On all those 15 machines, on each element of lines, two words will be executed. Okay, all right. Now Dia's point is it static equivalent of Java. You can think of it that way. Okay, because in case of Java, if you put something static, what happens is in all the functions, no matter where it's being called, the value is you know is common. Yes. So here we are using, as Aruna is saying, that here we are using two words uh, for filtering. So kind of yes, it basically we are saying that drop everything, return null, return blank if you don't encounter. If you if so Return empty if you encountered the, and that's all. So it's kind of way we are using two words as a filter also. So Vikas's question is, uh, does the other node completely stop processing if they see the boolean as false? Yes. So what happens is, since these things start happening parallelly, so there is always a minor delay. So it is not like 100% true. So if there is one file which has some lines, some lines being processed on one node, some line processed on another node, so there are chances that till the point the word goes out, the other nodes have already printed the words. Okay, so there is always this delay. You can try this out and you will realize that yes, there is a minor delay. All right, great. So this is okay. So you can think of myb as a static variable across the cluster. Good. All right, that's pretty much about Apache Spark. So the whole foundation of streaming, MLlib, uh, I mean SQL, Spark SQL, everything is based on these actions. All right, everything is based on these actions and transformations. Great. Now coming to Spark streaming. So Spark streaming is the extension of core Spark API. It's a high throughput for and it's very fault tolerant. So whenever you do processing, so remember that streaming is not your streaming like pig streaming or Hadoop streaming. Here streaming means that when there is a data coming in which is generated really fast and we want to process that data as it comes in, that is called Spark streaming. Okay, um, that's called streaming. Okay, let me repeat once again and give a better example. So imagine that you have got a Twitter account. Okay, and you're monitoring what is the in last 1 second, what has been the most popular keyword, or in last 1 hour, what is the most popular keyword. So what will you will do is you will keep on reading the data continuously from Twitter and keep on computing the uh, word count in the last 1 hour window, or 1 minute window, or 2 minutes window. Okay, this is called streaming. Or you can say stream processing. This is a stream of data that is coming pretty fast, and you want to convert that incoming data into the windows into a window of say 1 second or 10 seconds or so, And then for each of the window you want to do the computation. This is called streaming. Okay, one such application was what I had written. uh, Basically we had written our own stream processing platform at Amazon. So what we were doing is, whenever our vendors or anybody changes the data, we get the in our queue we get the data. Okay, we get the alert saying somebody had changed this particular page, somebody had changed that particular page, and so on. And this data keeps on coming really really fast, meaning every second there are 10 or more updates from our vendors and so on. Okay, so the data keeps on coming in a queue. Okay, in an organization when this kind of data need to be processed, they generally install a queue. Okay, there are really really powerful queues like Kafka and 0MQ. Flume and HDFS is just another example of the input data, but real queues are something like Kafka and 0MQ, in which the application from across the organization keep on dumping the data, and you have to, and there are multiple applications, not only your application, there are multiple applications who keep on reading the data from the queue. And this queue is really robust in terms of the way it stores the data, the way it handles the concurrency, meaning multiple people trying to read the same data, and so on. So whenever you have a queue or you have this data coming in really fast, you need to have a system which can consume the data from this queue and process it at a really fast pace. Okay. Now in my case, the one which we built at Amazon, this process of consuming data and doing churning was being done at 30 machines parallelly. Before me, it was done at around 60 machines, and after I did the implementation, we brought it below 30. Okay, so that is the role of stream processing, and the role of stream processing is that this data would be coming in. We convert that data into windows or batches of data. So this is how it looks like. So the data is coming from various sources. We convert it into batches of data and run our Spark code, whatever we action transformation on top of it, and give the results. So this is what happens in case of stream processing using Spark. Okay. So the central idea behind Spark streaming is a class called dstream, which essentially converts inflow of the data by creating resilience dataset on top of the incoming data. It breaks down the input data such that it breaks down the input data into batches. Each batch will become an element in your RDD. Okay, and for each element you can do the processing the way you always want it. And why is it done? Basically, what has happened is Spark was never planned to become stream processing engine. It's just that when people realize that the performance of Spark is really, really great, it's really fast, then they thought that it can be used for stream processing. So they wrote a wrapper such that incoming data keeps on getting converted into an RDD where each element is created out of the window. Window means a batch. I mean, from all the data that was retrieved from 0 second to 1 second becomes one batch, and hence one element inside RDD and so on. Okay. So as you can see, the data from time 0 to time 1 becomes first element, data from time, and so on. Okay. So then once you have created an RDD, then you can apply the transformation the way you always want it. Okay. All right. So you can see this. There's a this is how it's getting converted, and the window operation means there is an original stream coming in time 1, time 2, time 3, and so on. Out of this we are creating batches of elements. So from time 1 to time 3 we created one window, time 3 to time 5 we created another, and so on. So basically, this way we make our life easier by batching multiple records together so that they can be processed properly. All right. Okay. So any questions so far? So Kalyan's point is that looks like streaming and transformations are same. Yeah, it looks like that way, but if you look at it, basically the stream processing is composed of two parts. One is converting the inflow of the data into RDD. Okay, and that is done by convert batching the data together. So the way the flow will look like this. So data is coming at a very fast pace. Let's say from Twitter, the example we took earlier. So it will keep on accumulating data for first 1 second. Then we'll take this data and push it to RDD. Then we'll take another data from 1 second to 2 seconds. Then push it to another same RDD as a different element. Okay, and and then we can keep on processing this data as and when we want. What will be the real world implementation scenario for Spark streaming? Let's say you want to do a real time uh, processing of Twitter data, meaning you want to show a real time trend of something. Okay, you want to show per hour trend or say per minute trend of your product in the real time. So what you do is you you create a Spark streaming which consumes the data from Twitter and keeps on windows of data, and then you do a transformation of each of the batch created by dstream, and then you keep on displaying that how is whether your brand is trending or going down. So that could be a real world implementation scenario for Spark streaming. Make sense? All right. Now same thing. Let's say you want to count word every second that is coming from the input. Okay. Let's say you have put in a Twitter stream, as in you wrote a program which reads data from Twitter and is only giving you the tweets in which your brand is mentioned. Now you want to count words per second in the incoming data. Okay, so what you do is first you create a service which connects to a particular port wherever your queue is running, and you also define, so this Java streaming context, this is one class representing the D stream. Okay, this is a part of Spark streaming. Here, when you are initializing, you are telling few things. First is the name of your service. That's irrelevant to you right now. What is important is how big the window do you want. Here we are saying 1000 millisecond. So for each 1 second window, it will be for each 1 second window, it will be creating an element in RDD, and then it will connect to the service which is running on this particular port. Your queue might be running on 999 port, and once you're done with that, you can you will get once you have done that, you can basically start doing things like this. Okay, you can start reading the data from input and start processing it. Okay, so the way we have said lines equals to open the socket stream of a window of 1000 milliseconds. So on this line, which is basically an RDD, you can start doing things like flat map, map, and other things. Okay, and this will happen per second basis. For each second, whatever data is received, this will get executed only on that data, and it'll keep on getting executed again and again as the as the time progresses. Okay, that's what it means. All right. So basically here we are doing the word count, doing the first flat map, converting lines into words. Then we are converting word into a tuple. And then we are basically counting by using reduce by key, the way we did earlier. And afterwards, this will be the result. So the input stream will be converted into first batch where there'll be lines from first second 1 second, then second, the third second, then fourth second. And then when we do the operation, there'll be the result will be words from 0 to 1 and so on. Okay. So basically we were able to count words on per second basis rather than in the whole text. Okay, because in lots of scenarios it's not possible to keep on waiting forever. We want to process data as and when it comes, and that's what we are doing here. All right, so okay, so that was about Spark streaming. All right, so the processing is being done on one machine. Okay, the other RDD element could be on another machine or could be in the same machine and will be executed separately as a different process altogether. Okay, so say from 0 to 1 is being processed and from 1 to 2 is still being collected. Okay, so that processing will not start yet. While the processing from 0 to 1, this RDD element will start happening, the flat map operation. Okay, so uh, basically out of the incoming elements, we created these mini batches, and for each batch, we are running our flat all the transformation and all the actions. Okay, did I make sense, Vikas? All right. Any other question at this point? All right. All right. So this way you can utilize Spark streaming in a number of ways. And also basically similar to MapReduce's Hive, Spark SQL can also be utilized and in the same manner. All right. Good. Okay. So that's pretty much about Spark. Moving back to our Uzi. Okay, so in a big project you will have many things in parallel. Okay, you are or many things in series. So in a typical project, let's take a case of let's say, let me just increase the font. Let's take a case of recommendations. Okay, let's say you come up with the recommendation project. So first task will be to move the data from all web servers into HDFS. Okay, that is our first task. So are you guys with me? Amish, this is more of a from the project management perspective. Okay, not too much coding involved in this. So say let's say you are building a recommendation engine. Okay, recommendation engine is probably the easiest to understand because we have talked about it. Okay, so let's say we are building a recommendation engine, and let's say you are an e-commerce website. Okay, you are an e-commerce website. So this data like who visited which page, how much times, is a very important aspect. And you decided that instead of people's rating, you are going to build the recommendation based on who is visiting which page, how many times. All right, that's what you are planning to create. So let's say you are an e-commerce website trying to build recommendation engine. The first step would be to move all the data from all the web servers to HDFS. Okay, so the step number 0, which is done generally using a system like Flume, which will keep on absorbing all the data from web server continuously rather than waiting for a day or something. It will continuously keep on absorbing the data and keep on pushing the data onto HDFS. So this is done using say Flume or some other system. All right, now then is after the data has been moved, this will keep on happening all the time anyway. Next step would be to process PROs, process the logs, move the Apache logs. Okay, so any request that comes to your web server is actually recorded in logs, and I'm assuming that your server is having Apache web server, and therefore all this information is captured in the logs. Now process the logs and convert to user ID and product ID. Okay, now how would you do it? The easiest way to use MapReduce. Okay, for each line, for each line, you basically clean up the data. In case this line contains a user ID and a product ID, then you just process it and put it like a user ID and product ID. All right, now this way you have formed you have formed a simple, or let's say there is no reduce in this page. Okay, so you say here convert to tab this. Okay, once each line is converted into this format, now you can apply various kinds of processing using Hive/Pig. Okay, say you are computing user to user mapping and product to product mapping. Meaning, what exactly are you doing? For each user, you are finding how many times this user likes the product, as well as you are also computing if a user liked a particular product, which other products did he like? So that is called product to product mapping. People who liked this product also like that product. That is product to product mapping. Uh, okay. So this product, so this product was also liked by those people who liked the other product. So that is a product to product mapping. And user to user mapping is this user and this user is similar to each other. Okay, so those things you can do either in Hive or in Pig. And once you have done the cleaning of data, the other role of Hive or Pig could be clean up the data in number one to generate user ID, comma product ID, and third is rating. And generally rating is not given to you on a silver platter. You basically compute rating by saying this user has visited this product these many times. Okay, and therefore you keep on summing up. So you group by user ID and sum up, count how many times a particular product ID has come in, or you group by user ID and product ID and then count. Okay, and then whatever ratings you have come up with, you generally normalize rating. Okay, normalize the rating. So you can see that we can convert the data which has come in the step number one to generate user ID, product ID, and normalize rating out of 5. Okay, okay, normalized rating out of 5. Now next step to Hive is running Mahat on the data generated in on data of step number 3. Fifth is using scoop, move the data from step number 4 to MySQL of our web server. Okay, so if you see these steps like 1 to 5 are something that needs to be executed in a sequence, and these need to be done every day. All right, is it clear to everyone what we are doing here? Since we have gone through the full loop, we should be able to figure this out. So is it clear or is there a doubt on any of the points? Data from step number 4 and step number 2. Okay. So the goal here is to build a recommendation engine like Amazon. Okay. You are an e-commerce company and you want to give recommendations something like top N products of the year, or people who bought this also bought this. Okay, this product goes along with that product. Also, what the goal here is to find out the proper recommendation, as in you may also like this based on your past history. You may also like this. All right. Now, Sandhya's question is, can you please repeat the role of Mahat? Mahat, what Mahat is doing, based on this data, that this user liked this product this much, it will give you the recommendation that this user would like this product this much. That is the role of Mahat here. Okay, the way we did our movie recommendation, in the same fashion we are doing it here. Make sense, Sandhya? Should I? Mahat basically would generate, cluster the users, and do all sorts of uh, mathematics to figure out who are the similar user like yours, so that it can do a re- cross recommendation to each other. Okay. No, this is not, Mahat is not a in-memory engine. Mahat basically uses using MapReduce underneath. We are going back. We are done with Spark, so we are going back to the very usual MapReduce. Here, Mahat runs on the MapReduce, the usual one. Okay. So are these steps clear to everyone? Great. Now, okay. So these are normal flow what we do in case of a recommendation engine, and it's a very common thing. And in case you are part of an e-commerce company, you can straight away, or if you have good enough traffic on your website, you can straight away start preparing a similar kind of recommendations. All right. So these are few things, and as you can clearly see that we have used multiple products in case of a single project. Okay, and whatever we are comfortable with, we basically go with those kind of tools to get our work done. And therefore it is important to be able to integrate all of these tools together, and that's when our Uzi comes into play. Okay, so Uzi is a workflow scheduling system to manage Apache Hadoop jobs. Okay, so each steps what we just discussed would be a job in itself. Okay, or will be a part of the single job and will be a task. And the way we define a workflow job is, it's basically a DAG. DAG is directed acyclic graph. Okay, so whenever we, let us say, let's have a look at this diagram. Okay, so this diagram says that task number 5 should be done after 11 has finished, and 11 can only be done after 2, 9, and 10 has finished. Okay, so this is so, and similarly here, task number 3 can only be done after task number 10 and 8. Similarly, task number 7 can only be done after task number 11 or 8. So this kind of graph or dependency chart is there in every day of our life. Whether we are compiling our usual Apache Ant or Maven or Make, or we are a project manager and we are creating a project plan, we create the dependency of tasks. Okay, so whenever there is a directed acyclic graph, meaning there is no cycle, meaning A depending on B depending on C depending back on A. When this kind of dependency is not there, we call it a directed acyclic graph. Okay, and this is everywhere. So directed acyclic graph as a computing data structure is used at a lot of places. And same is the case with Uzi. And as a matter of fact, it's actually simple thing. It's like saying, to get ready to office, I need to wear my glasses. wear my shirt, wear my trouser, and and shoes. Okay, so I can't wear shoes before wearing the trousers, right? Otherwise, it'll be a problem. And to get ready and to wear clothes, I need to get take a bath first. So all of this, if you try to draw it, it'll become a complex workflow graph like this one. Okay, so Uzi is basically Uzi executes the jobs, and each job is a directed acyclic graph. And there is something called coordinator, which basically executes these jobs at a particular schedule. Okay, you can you can trigger a particular job either on a frequency or on data availability. As soon as the data is available, please start my task. So that kind of dependency also can be created. And Uzi is integrated with the rest of Hadoop and is really scalable and extensible. All right. So uh, this is how a typical Uzi workflow looks like. Okay. Let me create another. Okay, this is how a typical workflow looks like. Although there is a UI, we will also show you the UI, but let me just try to show you in XML how does our typical task looks like. Okay, so just like our ant scripts, you you have something called an action. Okay, you have something called an action, and in every workflow, so every workflow application starts with workflow and workflow, and there is an entry point called start, and to which you define the name of the action, which is your entry point. So this is your action, which basically is doing the word count. And how is it doing word count is by using map reduce. Okay, by using map reduce, and under map reduce it defines the job tracker and name node, and then the rest of the properties. Okay, as if you are trying to execute it from the command line. All right. Okay, and here we are saying that in case the job is successful, send it to go to end. If the job is failed, then go to kill. Okay, so if the job fails, it'll come here. If job is successful, it comes here. Okay, that's what we are saying. So start, do the map reduce count. If it fails, go to kill. If it successful, go to end. Now, the workflow could be complex like this one. Start, then fork, and then in the fork, you create these two tasks, second and third, and then you have something called join, and then we'd go to end. Okay. So when we are talking about our problem, okay, like this one, so we can here, let me, okay. So here, uh, so the step number one is not required, okay, because this is happening every minute. But okay, so after step number one, which is processing the logs, and step number two, okay, now hive and pig can execute only if the step number one has finished, right? But the step number three, which is cleaning up, can also happen parallel to the step number two, right? So step number three would look like this. Okay. Now step number four, which is moving data to step number three, of step number three, would depend on step number three, right? Okay. Now step number four, which is moving the data from all of these steps would depend upon, okay, so it'll look like. So now you can see this. So this is our dependency graph. So step number 2 and 3 can be parallelized. So therefore, this kind of complex structure in case of Uzi is very, very useful to us. All right. And you can look at this XML and you can define this XML that these are fork, this is join and so on. All right. Now, instead of typing all of this XML, we can actually create this whole workflow in the web application. So we'll just log in into Hue. Okay, so we go to our editor dashboard. Looks like Uzi is off. Let's try to start the Uzi. Okay, so Uzi is off. Let me. All right. So here on Uzi dashboard, still starting. All right, I think it is started now. All right, so here you can create your own job. So you can create your own workflow and give it a name. Let's call it 30 June, 30 May. Okay. And in this, you can basically say, if you have the way we were doing the drawing. So first is your map reduce. Okay. First is your map reduce. So you take your here map reduce and drag it. Okay. Then you define my map reduce and whatever, and you basically I just want to upload any data. Or let's just upload here. Okay. Where was my download? Okay, I don't have one. It's not able to find it. Anyway, need to user student, and there will be somebody's map reduce. I'll just pick anybody's map reduce. Oh, we don't have. Let's say I'm just putting something. Okay. So training 2, this is my map reduce and okay, and then done. So ideally you will be defining all the things in detail, but just for the example's sake, once you have done with map reduce process, step number 2, which is Hive or Pig. Let's say we have written our script in Hive. Okay, this is my Hive script and some Hive script. Let's say, okay, I don't have. I'm just trying to figure out what can be done. Okay, actually I had map reduce. All right. So let's say I'm just putting some file and this is my Hive script, imagine. And then I'll take Pig and drop it on Hive, or let me just, what is the other one? Yeah, other one is again Hive, and this is my second script. All right. Or we can even say things like pick up this. Yeah, so cancel it. So you can see that Hive script, second Hive script. And once that is done, we'll execute fourth, which is Mahat. And for that, you have to drag and drop maybe a generic one. All right. All right. And so where is the, yeah, this is my map, not this. I want it to be here. Okay. So I'm trying to replicate whatever we have done. First step, second, third, fourth. Now fifth step is here. Fifth step is what? Using scoop. Okay. So we take scoop here and say my scoop and say export something. All right. So you can see that we were able to drag and drop things and were able to make this workflow. It means it will do the map reduce first. Once it has finished that, it will execute this side as well as this side together. And after this, it will execute this. And once both the sides are done, then scoop query will be run. All right. So it is saying could not save the workflow. Yeah, maybe some it requires some more parameters. So yeah, if you specify all the values properly, like all the map reduces, uh, I mean all the classes correctly, you will be able to save it and get it done. All right. So this is how you generally plan. This is how you generally plan your project. Okay. Yes. Okay. So you can basically straight away drag and drop things and okay. You don't have to type and so from here itself, you can directly submit and it will start getting executed. All right. So that was pretty much what I wanted to discuss about uh, Uzi. and rest of Uzi we can discuss it tomorrow. All right. So if you have any questions, feel free to drop me an email at Hadoop and No Big Data, and I'll respond to Kalyan's questions. I mean, regarding the review, we'll just do that. Okay. And anything else do you want to ask? All right. All right. Thank you, Amish. And thank you, everyone. I hope you liked the session. Thank you, Kirti. Assignments are getting reviewed, and most of your assignments would have already been reviewed. I'll have a look at it, what all has been left. Okay. And try to answer as soon as possible. Okay. At least all of you, please finish the quiz. Okay. Finish the quiz at least. All right. So tomorrow we will be describing what does project looks like, and then we can discuss. Okay. All right. So tomorrow also we have one more class. That will be last session tomorrow. Okay. All right then. Thank you very much. Have a great day ahead. Bye bye.